Hi, this is Dave Lipscomb. I am teaching 6M6 lesson 8 and 9, mean absolute deviation from Engage New York and um, Eureka Math. So we're going to learn today about the importance of a mean absolute deviation, exactly what it means and how you calculate it. So let's see if I can successfully switch to another window here and get this going. Good. Okay, so we are going to be talking about mean absolute deviation. Now, in this lesson, you learn, or we see some data. And again, we've already learned about mean. And the mean is a calculation, the mean of a data set is equal to the sum of the elements divided by the number of elements. So for example, the mean of the data set containing 1, 2, 3, 5, and 9, we would find the mean to be 1 plus 2 plus 3 plus 5 plus 9 over the number of elements, which is 5. So we get 1 plus 2 plus 3 is 6, plus 5 is 11, plus 9 is 20, divided by 5. So the average, or the mean, is 4. Another word for the mean is average. Okay, so that's what we learned. This is what I'm going to kind of put that to the side. This is prior learning. Prior learning. Okay, so now we're going to learn a little bit more about data sets. Let's take this to the next level. So we're going to talk about the mean absolute deviation. Now it turns out, and we learned this from the lesson that you heard in class today, lesson 8 and 9 in Engage New York. And we looked at this interesting fact that in New York City, if we look at the average temperature across the year, they had a data set that was comprised of 12 different numbers, one representing each month of the year. And the average was, if the average was 63, the mean, or the average, the mean temperature was equal to 63 in New York, and the mean temperature in San Francisco was equal to 64. So the mean was right here on the data set in New York, and the mean of the data set was right here in San Francisco. So the mean is almost the same, but we learned that the data set in New York, the data was way more, this was more spread out. And in San Francisco, it was all clumped together. So I don't know. So if I told you the average or the mean temperature in a city was 63, you wouldn't really know whether you were getting this high variability or this low variability. This is a high variability, and this is a low variability. And we can see that. Now, what the mean absolute deviation does, and let me just put this in the same color, just so you can kind of see it, is the definition, is this tells us how variable, or the mean, how variable or how clumpy towards the middle, how clumpy the data is, right? This is clumped together and this is spread out, and we can see it visually, but we want a mathematical way of finding this out. And what the mean absolute deviation does is tell us just that. So let's just see how we do that. So there is a calculation that you can do that will tell you how clumped or how variable, what is the deviation in the data. So we have this concept of the absolute deviation for any data point, and we'll talk a little bit more about that here in a second. But the first thing I want to do is I want to remind you that the mean of this data set, the mean, sometimes when I write, the pen works a little weird. The mean is the sum, and if you add up, I got on a calculator, and the sum of all these numbers is 7. Whoa, see that happen? I got to do it like this. 756. That's the sum, and the number of numbers is 12. And if you do this on a calculator, you get 60. You get 63 degrees. So that's my mean. Or in San Francisco, the sum was 768. And if you divide that by 12, you get 64. So the means were almost the same. So now I want to show you how to calculate the mean absolute deviation. So to calculate the MAD, you find the deviation, wow, you find the deviation of, wow, this pen is kind of wonky today, of each element from the mean So we're going to find the deviation of each element from the mean, and then we're going to find the mean of all deviations. I need to fix my pen setting really fast here. That's my problem. Let me see if I can do this real quick. I got a pen setting. I'm going to try and set it really quickly. If I can't do that, I'm going to come right back. Okay. Okay, I'm not sure if I can do that. I'll try that next time. Okay, so we're going to find the deviation of each element from the mean, and then we're going to, let's see, what color should we use here? Let's use orange. Okay, and then we're going to calculate the mean average deviation, and we're going to find that it's going to give us this number that's going to show you that New York City, remember, it has a high deviation. It's a high variation, right? It's high variation. It's highly varied, right? The data was way to the left and way to the right. In San Francisco, we're going to see that we have a low variation, and this number is going to tell us that. That's the whole point of this calculation, to show that we have a high variation and a low variation data. So how far, so what we do is we first, remember, we find the mean, which was 63 for New York City, and we're going to figure out how far each of these numbers is from 63. So how do you find how far 42 is from 63? You say, well, 63 minus 42, well, that's 21. We say 63 minus 50, well, that's 13. 63 minus 61 is 2. Now, when the number's higher than 63, we don't say 63 minus 71. When the number's higher, then we turn around and we say, well, 71 minus 63. We don't care if that number's positive or negative. We just want to find out how far the number is from 63. And that's why they call it the absolute deviation. So that's like an absolute value. If it doesn't matter if it's negative, if it's negative, we make it positive. If it's positive, we leave it positive. So in June, 81 minus 63 is 18. July gets really hot, 85 minus 63. So this one's 22. This is way off of the mean. 84 is 21 off the mean. 76 is 13 off the mean. 65, we're back close to the mean again, which is 2. Then in November, it's starting to get cold. That's 8 off the mean. And in December, we're 16 off the mean. We're at 63 minus 47. All right, so now we have all of these numbers, 21, 24, right? They did this calculation for us, 24, 21, 13, 2, 8, 18. So let's add up all these numbers. So let's see, 24 and 20, here, let's see if we can erase for a second. Oop. Well, that's not very good. We'll just go ahead and use our pencil, and we'll just switch colors over to, say, fuchsia. Okay, so let's add up all these numbers. So these numbers I'm just going to add up all 12 of them kind of in a fast way. That's 45. These two added together, 15. These two added together, 26. 40. You could add all these up together on a calculator. I don't have my calculator handy, so I'm just going to show you how we add quickly. 24, 45, and 15 is 60. These two added together is 69. These two added together is 39. Now we're going to add these two together, and we get 129. And these two added together is 129, and 39 is 168. So that's the sum of our absolute deviations, but we want to find the mean. So if we want to find the mean, is we add all 12 numbers together, 168, and then we divide by 12 because there's 12 numbers. So now I actually am going to go find my calculator, and we're going to type in 168 divided by 12, and we get 14. So our mean absolute deviation is 14 for this data set. Now let's do the same thing for San Francisco. In San Francisco, everything's a lot closer together. So we expect a number that's a lot lower than 14 to represent our deviation. So let's do that. So 64 is our mean here. So 64 minus 57, that's 7. 64 minus 60 is 4. 64 minus 62 is 2. This is 1. This is 0. That's exactly the mean. This is 67 minus 64. Remember, when it's higher, we subtract this number minus the mean to find our absolute deviation. 4, 6, 5, 1. 64 minus 63, and then 58 is 6. So now if we want to add all these numbers together, this one we can do really fast. Okay, and you can just add all these together with a calculator. I'm just doing it this way because it's easy for me to do in my without going to the calculator. So that's 42. That plus that plus that equals 42. And 42 divided by 12, well, that's 3.5. Okay, so we get a very high, so here's the idea. So if our mean is 63 and 14 is our MADD, and here our average is 64 and our MAD is 3.5. Let's just go back and look at our initial data set here. Right? So we said this is more spread out. And what represents the fact that this is more spread out, we'll say, the way that we describe it is we say, well, here our mean is 63 and our MAD is 14. Whereas down here, our mean is 64 and our MAD is 3.5. Our average distance, the average distance from the middle is like 3.5. Up here, our average distance from the middle is it's 14. So our average distance from the middle does that make sense? Here's our average distance, a lot bigger. Here, our average distance is pretty close. So with that, we will, we're gonna, let's see, we'll come back to here. Hopefully this was a helpful video. It explained the mean absolute deviation, and it showed you how to calculate it using an example that we learned in class. So until next time, we're signing off. This is Dave Lipscomb.